The main function of the battery ECU is to monitor and report the condition of the high voltage battery pack to the hybrid control ECU. A second function is to monitor and control the battery pack blower motor in order to maintain the correct battery pack temperature. The battery pack ECU also sends messages through the gateway modules to the AC amplifier, air conditioning amplifier, to cool the cabin air. If cabin air is being pulled by operating the fans and the cabin air isn't cool enough, it's too warm, the battery ECU will go through the gateway and tell the AC amplifier, hey, turn the air conditioner on. The AC system will cycle on if the cabin air is too warm for battery pack cooling requirements. Here's a good line drawing of the battery pack assembly with the cover off. And there it is with the cover on. You can see that we have a battery ECU, and there it is right there. It's disconnected. It's going to be removed in this particular vehicle that we were working on. As we look at that right there, you can see one connector. Later on we're going to show you an image that shows both connectors on one side and a single connector on the other. It has the service plug. Now the service plug, when you're standing at the rear of the vehicle with the hatch open and remove the carpeting and the cardboard cover, you see the battery pack. Look to the left hand side, you can see the orange down there. That is the safety switch, and there it is right there, and there's the cavity it goes into, and when you put it together it looks like that. And the two wires, they travel down the battery pack modules and they connect on a 1B and a 1 negative module. Now that tends to be very close to the center of all the modules. Now in this photograph, when you look to the right, it looks like we're out of modules, but that's because they're missing. They have been removed while we were working on them when we took this photograph. So that safety plug goes to the center of the battery pack, as you can see in this drawing here. We have the battery modules on the top and below that red arrow showing the service plug. Now it has main battery cables, and they run to the power relays. Here we're showing you the battery temperature sensors. There's 3 of them there, and they're normal everyday sensors we've been working with for years. There's a photograph of a battery pack showing you the three sensors, and then in the lower right hand corner we have one of the sensors removed to show you that it's really just a temperature sensor, an everyday 2-wire temperature sensor. We have a battery current sensor, so we can sense the current going in and out of the battery. Here's a line drawing showing that, and there's your sensor exactly, and that is a real life picture of your sensor right near the power relays, and the green arrow is showing that the one power cable goes through there, so we can measure current going out and in the battery pack. The battery ECU is going to communicate with the hybrid control ECU, the internal combustion engine ECM, the gateway module, and it's going to do this via the CAN network. We can see that we're pointing to the battery ECU, and it's going to talk to these modules on the CAN bus. It's going to do voltage detection. Now look at this photograph. Just right in the center we have a battery ECU. Coming down we have VBB 14, 13, 11, 10, and a 981. And They just, in this drawing, didn't put all of the modules in there. It's 1 through 14. The VBB1 is the very first module, and then the VBB14 would be the last. This drawing just doesn't show all of them. Just take all that. Now, if we look at this drawing for a minute, it's pointing to a wire with an eyelet on it. That is on a positive side of a module. Go to the left there and you can see that we've taken the nut off. Every positive side of the module on this side of the battery pack is going to have a voltage sense circuit there. Now this voltage pack has been cut for demonstrations in a classroom. So when you look to the left, you don't see the other modules. This was for demonstration in a classroom. And here are the buses that connect positive to negative when we're talking about the 6-cell module. So we have voltage sense and the bus connectors. Let's look at that. The GBB0 is the one end of the battery pack, and VBB14 is the other. And what happens there, we have a negative GBB0 going to the battery ECU on the voltage sense. And then we have the VBB1 through 14 being VBB14 is at the other end. So we have the modules connected in series. One end, they call it V or GBB0. At the other end, it's VBB14. 6 cells make up a brick. 4 bricks make up a block. So 6 cells in one module, and they call that a brick. When they put 2 bricks together, they call that a block. Now that information is critical for understanding some scan data PIDs. Each cell of the battery is going to produce about 1.2 volts. If we have 168 cells connected in series, we're going to produce about 201.6 volts. The battery has to be kept cool. So Prius put a blower motor in, and we're going to have blower motor control by the battery ECU. Here we're showing you that we have a battery blower motor controller, and it's connected to the battery ECU. On the left hand side there at the bottom, we're showing where the cooling fan is on a car. Now the battery ECU is going to calculate using the state of charge, the current flow that goes through that sensor we showed you in and out of the battery pack, temperature, those 3 temperature sensors we showed you, and then it reports to the hybrid control ECU. As it does that, it sends a signal from the battery control ECU IB circuit to the hybrid vehicle control ECU, the IB circuit. And so it's going to report this is a circuit that the battery control ECU is talking to the hybrid control ECU about all those things. The high voltage diagram starts with the high voltage battery pack modules. There is your battery pack right there. Then it goes through those relays that we've shown you, and it has a frame wire so it can run up to the inverter converter assembly, and your frame wires simply go all the way up to the front there. And this is where it goes to the inverter assembly, inverter converter assembly, and that's the unit that has the boost converter, the motor control, and the AC inverter built into it. And there it is with the cap, the cover off, and on the right hand side the arrow's pointing to where those frame wires come all the way up to the inverter assembly from the back of the car. And then of course the high voltage diagram ends with the high voltage 3-phase circuits going to motor generator 1, 2, and the AC motor. And there we have our what's called UVW, 3-wire, 3-phase circuits going to the motors. And there it is on the other half on the transaxle where the motors are assembled with the transaxle. Now, fail-safe. There has to be a fail-safe if there's a problem that can damage the very expensive battery pack or modules. The battery ECU goes into a fail-safe mode, sends an alert to the hybrid control ECU if vehicle operation needs to be changed or altered. The key items to understand is that voltage is going to change with the state of charge. Nickel metal hydrate cells have a smaller variation than what we're used to, lead acid batteries. The state of charge is a critical measurement that's going to involve charging, the temperature, and the voltage. So as temperature changes, battery voltage pack changes. As charging rate, the voltage in the battery pack changes. So as these things change, we have a living and breathing PID called the state of charge. It's never going to stay at one position. Now, the minimum, and the maximum state of charge are not the normal state of charge. Right now we're talking about the maximum state of charge. We're not talking about what's normal. We're just saying, hey, the maximum. The operation outside the 2080 charge level can result in an increase in heat and internal battery pressure. And then pressure venting is going to occur if we keep the heat up. Now this is the maximum state of battery charge, 80%. What's needed is a much narrower range than 80-20 with a controlled environment to increase battery life. A key phrase here, controlled environment. The battery ECU will manage the temperature and the state of charge. The state of charge has a big impact on battery heat. Deep cycling will shorten the battery life and probably damage the cells. The battery ECU manages battery loads and recharging to manage the depth of charge. State of charge must be controlled for the maximum battery life. Not allowing it to go too low in the depth of charge is going to help us get the maximum battery life. So the battery ECU is going to manage the loads. When we said that, what we meant was, we know that a hybrid, for example, when it's accelerated, it starts to move on 100% electric. Now, if there's something wrong with the depth of charge or the state of charge, they're too low, the battery ECU tells the hybrid control ECU, and the hybrid control ECU starts the ICE and doesn't give us electric drive. And we'll show you a chart here in a minute, and in some cases it'll limit how much electricity goes to the motor, and in some cases it won't give any electricity to the motor. So it's not going to allow it to go too high either. A safe discharge voltage of 0.9 volts, and that's 75% of the 1.2 nominal voltage for each cell, which is 5.4 volts for that 6-cell module or a brick, and 10.8 volts for a 15-volt block. This is the maximum operating range, but operating in this range would shorten the battery life. Overcharging will cause an overheat condition that can cause the battery internal pressure to rise too quickly. Attempting to increase the percentage of the charge would cause the battery voltage to drop, which could lead to thermal runaway. Venting of this gas. Now, gas venting is caused by overcharging, and the gas vent is built into the top of the 6-cell modules. One's a male, one's a female end. The damage to the battery cell is likely to be catastrophic if the battery being damaged is no longer serviceable. The gas from the vent goes into that vent tube, and here's our two vent tubes right here. The battery control ECU is going to stop charging the battery at 68% state of charge, and that's what's normal. I don't want you to get the idea that you're going to look at state of charge on a scan tool and never see it over 68%. There are way more incidents than we can talk about and conditions, and we said that operating between 20 and 80% is what it does. The normal is 52 to 68%. So the battery ECU in normal conditions is going to stop charging the battery at 68%, with 52 to 68 being normal and 60 being the ideal state of charge. But that's not what we're going to see, because it's just not going to be able to stay there. We're going to use some current, give it some current through charging, regen. It's going to change. So what it's really going to do is flow up and below that ideal 60% state of charge. 52 to 68 is what's normal. Now, because the battery ECU is controlling charging and discharging, it's going to control the cooling fans. The fan is speed regulated to reduce noise when the vehicle stopped. So let's look at this blower motor circuit. We have the battery ECU over on the right hand side there. Now, this wire going from the battery control relay to the battery control ECU is the fan relay control circuit. It's going to be controlled by the battery ECU. That circuit is designated FCTL1. The FCTL1 signal is used to control battery blower relay number 1 that supplies B+ to the fan motor. Now, you can see the circuit goes from FCTL1 to the blower relay and through that coil there. That closes the blower relay and completes the circuit to the blower motor assembly itself. FTC circuit is a low side driver, meaning that the transistor supplies ground to energize the motor, which the motor already has B+ on it. The power is supplied by the 12-volt battery, and you can see that it's always there. There's no switches, just some fuses. So the battery ECU controls this circuit power to the blower motor through the blower battery relay to ground. The ground side voltage is monitored by the VM signal at the battery ECU. So it's going to have a diagnostic circuit with it. The B+ terminal is connected to the battery blower control unit, as we see here. The SI signal in the battery control ECU is a duty cycle type signal, and it duty cycles the signal to ground, and it grounds it, ungrounds it. So it's an on and off signal, and that's what regulates the fan motor speed, this SI signal right there. The VM signal is connected to the blower motor itself, and we'll draw that for you. It goes up to this transistor and just stops. But you can see the SI signal in the battery control ECU is going to turn that on and off, on and off. And that's how that SI duty cycles the blower motor itself, by turning the ground on, off. The battery pack temperature is very important. The battery ECU controls the fan based on the temperature of the battery pack based on the battery pack temperature sensors. The battery ECU will start the battery cooling fan at somewhere around 77 degrees Fahrenheit. At 77 degrees Fahrenheit to 122 degrees Fahrenheit, the ECU will run the fan at maximum speed unless it causes a noise problem for the passenger. So when the vehicle's in gear at a stoplight, it's going to change the speed. The fan will run only at max when the vehicle is moving, and the fan noise won't be noticeable. At over 140 degrees Fahrenheit, the battery ECU will shut down the HV battery pack. The battery current sensors have to be monitored also. They're Hall effect battery current sensors. They have a calibrated voltage scale that can detect charge and discharge currents. If the signal voltage is under 2.5 volts, the current is discharging the battery. If the voltage the battery ECU sees from its current sensor is over 2.5 volts, the current is charging the battery. The signal voltage of 0.5 volt indicates a 200 amp discharge, while an output voltage of 4.5 volts indicates a 200 amp charging rate. The battery ECU uses this data to control charging and discharging voltage, and you can see battery pack current in scan data. Now, it does all of this so it can control what's happening to the battery pack. At 6% state of charge, all vehicle operations are shut down. This vehicle isn't going to be going anywhere. At 35% state of charge, the electric traction motors are shut down, meaning that you're not going to have any electric sys, only ICE. At 40%, the electric traction motor use is reduced. And that means that instead of getting boost, instead of getting all of the electric motor assist, it's going to reduce it. At 50% state of charge, the internal combustion engine starts to recharge the HV batteries. And this is the easiest thing in the world to see. When you walk up to a hybrid that's been sitting around for a while, overnight or all the day, what happens is you plug in your scan tool and you look at the state of charge, and remember, you're inside the battery ECU to get that state of charge, and when it's 50% or under, and what happens is the ready lamp comes on the dash. And almost immediately, within seconds, the internal combustion engine starts up to recharge the HV batteries. And that's why, because the battery pack controller told the hybrid controller that it was under 50% charged. 52 to 68% state of charge is ideal operating room. Now at 80% state of charge, regenerative braking is stopped. It's not going to put any more charge or battery charge into the battery pack. At 94%, that's like 6% at the top. All vehicle operations are shut down. 52 to 68% state of charge is the ideal.